try to integrate these or to find the volumes here, I'd like for you to tell me, or let's walk through together, how we would set up to find the volumes rotating the regions that I have shown here around the y-axis. Okay, what would be a problem for us to rotate this region around the y-axis using the methods that we know? Now, I'm not saying we can't do it. I'm just saying it could be kind of painful. If we are rotating this one around the y-axis, we would have to use horizontal rectangles. Yes? So the problem is, one way or the other, I would have to set up two integrals. Because above this point, it's no longer a disk method, it becomes a washer method. Now, granted, for the bottom part, it's just a big flat cylinder, so you really could get that part of the volume using a geometric formula, but if we're doing it just kind of by brute force, we would have to set up and go, okay, first thing, I'm going to have two sets of integrals, and the second thing is I also have to simplify this and write y equals the square root of x squared plus 1 as a function of y rather than x. So this would be y squared is equal to x squared plus 1. So x squared would be y squared minus 1, or x would be plus or minus the square root of y squared minus 1. And then we still have to decide, well, do I have the plus square root or do I have the minus square root? In this case, since the function is to the right of the y-axis, we would have the plus side. Okay, so we've got that part. The lower region, if we were going to do it with integration, would be a disk problem, and it would be pi times the integral from y equals 0 to y equals 1. What's the radius from here to here? Well, it's just that horizontal distance. This is defined to be x equals the square root of 3. This is x equals 0. So that radius would just be the square root of 3 minus 0 squared. And our rectangles or thickness is horizontal dy. So that would give me the volume when this rectangle is rotated around the y-axis. Then for the upper part, we would have to do pi times the integral from, okay, what's this point? They kind of told us, here that that's y equals 2. You could also find it by plugging in the square root of 3 to this graph, which would give you the square root of 4 under equals y. So it is 2, but we'd be going from 0 to 2. From 1 to 2, yes. Then we would have the outer radius being what? The outer radius would be from here back to the axis of revolution. That's right minus left is the square root of 3 minus 0. And the inner radius would be this distance. And that distance is the square root of y squared minus 1. And technically it's a minus 0 over there. Let me put that for emphasis. Right minus left. So, can I do it that way? Sure. Is it kind of a painful process? Absolutely. But we could. Okay? Now, I'm going to leave this for time's sake, and we'll come back and look at it again in a different way. What about this one? Now that's an x cubed, even though that's kind of hard to read. That didn't make it any better, but okay. If we were going to integrate this one, going around the y-axis. Well, who wants to solve this for x in terms of y? No one. Exactly. So it's just not even really reasonable that we're going to have to switch the order of the variables in that problem. So what we're going to talk about in this section is, sometimes it's doable but not convenient to use rectangles that are perpendicular to the axis of revolution. And sometimes it's either impossible or feels impossible. So in this section, we're going to talk about what happens when, instead of rotating rectangles that are perpendicular to the axis of revolution, we rotate rectangles that are parallel to the axis of revolution. Now, when you rotate a rectangle that is parallel to the axis of revolution, you cannot use the disc or washer method, because if this rotates 360 degrees around that axis, it doesn't form a disc or a washer. What it forms is a cylinder. Now, it only forms the wall of that cylinder. Okay? So think of these kind of as, what I would say is nesting dolls. So we would have another slightly bigger cylinder out here, and they're just kind of forming one big solid. So what we're going to work on doing is finding the volume of those cylindrical walls, or what we call cylindrical shells, and add them all up using integration. Okay? So how do you find the volume of a cylindrical shell? Well, think about this. If I took this piece of paper, and I know it loses something when you're looking at a picture on a screen here instead of being in class, that could form a cylinder. Okay? What we're looking for here is the volume of that piece of paper forming the cylinder. If you take a rectangle that is parallel to the axis of revolution and you rotate it and form a cylinder, how would we find the volume of that wall of the cylinder? Well, if you take that cylinder and slice it, what do you have? You have a rectangle. So you take a cylinder and you just slice it down the side. It just folds out into a rectangle. So what we want to know is, what's the volume of that piece of paper that formed that cylinder? Well, the volume of a cylinder is the area of this rectangle times the thickness of the piece of paper or the rectangle. The thickness is always still going to be dx or dy, but how do you find the area of that part? Well, the distance around the cylinder would form this length on the rectangle. The distance around a cylinder is called the circumference, since it's circular. So that distance right there would be 2 pi times the radius. And this would be the height or the length of the rectangle that was being rotated. So to find the volume of a cylinder, you take 2 pi times the radius. Now remember, the radius is always a distance from the axis of revolution. For cylinders, the radius is going to be the distance from the axis of revolution out to one of your little rectangles. Okay? So it's going to involve either an X or a Y, and we'll talk about that more in detail in just a moment. But if we add all those up using integration, the volume using cylindrical shells is found by taking the integral from A to B of 2 pi times the radius times the height times the thickness. Now, in the cylindrical shell method, the radius will always look like either x minus the axis of revolution, or the axis of revolution minus x, or the analogous statements involving y's. Because, well, we'll see that pictorially. The height that we're talking about in this formula is just the height or length of the rectangles being rotated, and the thickness is still dx or dy. Now, if you are using rectangles that are parallel to the axis of revolution, you must use the cylindrical shell method. And on the flip side of that, to use the cylindrical shell method, you can only use rectangles that are parallel to the axis of revolution. If your rectangles are perpendicular, you must use either discs or washers. What this does is it gives us choices. Choices make life better, choices make life harder. Because we're going to have to decide in general, would this be easier to integrate with respect to x, in other words using vertical rectangles, or with respect to y, which would mean we were using horizontal rectangles. So let's look back at those two that we just discussed, the issues using horizontal rectangles, and let's look at using vertical rectangles. So this graph, if I want to rotate around the y-axis, my rectangle is parallel to the axis of revolution, so I'm going to need a thickness, a height, and a radius. Two reasons I usually start with thickness first. Thickness is the easiest. It's always either dx or dy. When my rectangle is vertical, what is it? Dx. Good. The height is just the height of that rectangle. In this case, it would be a top graph minus a bottom graph. So that would be the square root of x squared plus 1 minus the bottom graph of 0. So it's y equals x squared, square root of x squared plus 1 minus y equals 0. Now the radius. When this rectangle rotates around that axis and forms a cylinder, the radius is this distance right here. It's always the distance from the center of the solid, which in this case, it will always be the axis of revolution. So how do we figure out what this distance is? Well, it depends on where your rectangle was, right? This little rectangle just sits on some representative x value in the interval from 0 to the square root of 3, and we'll catch all of them when we do the integration part. So this distance right here would be right minus left. This is just some x value. This is x equals 0. So right minus left would be x minus 0, or it's x minus the axis of revolution. So our volume here would be what we get when we take 2 pi times the integral from, in this case, my limits are my x limits on my region, and they go from 0 to the square root of 3. And it doesn't matter if you put this 2 pi out front or inside the integral, that's fine. But we have 2 pi times the radius times the height times the thickness, which is a much quicker integral to do than setting it up in terms of two separate integrals that we did in the first method. Questions so far? All right, so let's do the same for this problem. I want to use x's because I don't want to change that 9x over the square root of x cubed plus 9 to something in terms of x as the or y as the independent variable. So for this one, I want you to think about it for a minute, and I want you to identify what you think are the thickness, the height, and the radius for that graph. Now keep in mind, when that rectangle rotates around and forms this cylinder, this distance is the height, this distance is the radius. So I want you guys to think about it for a couple minutes, write down what you think it is, and then when you're ready for us to discuss it, if somebody would, type in, done or something like that into the chat so I know that you're ready to look at it. All right. So who wants to tell me what the thickness is? dx. Excellent. The height, just this distance right here, top minus bottom. Did you guys get 9x over the square root of x cubed plus 9 minus 0? Yay! And then the radius, remember this sits at some little x value between 0 and 3. So this distance would be right minus left would just be x minus 0. And that volume would be 2 pi times the integral from 0 to 3 of the radius times the height times the thickness. Or if we needed to integrate that, that would be 2 pi times the integral from 0 to 3 of 9x squared over the square root of x cubed plus 9 dx. Now I could go ahead and factor out that 9 or leave it in and use part of it. I'm going to go ahead and factor it out. Even though I will want part of it back here in a minute. But then to integrate this, we would just use u substitution with u equals x cubed plus 9. Okay. So since I've already factored out my 9, I'm just going to go ahead and multiply 3 and reverse with a 1/3 out front. I could have left part of that 9 in there to take care of that, but 6 of one, half a dozen of the other. So we end up with 6 pi times the integral from. Do you want to go ahead and change the limits of integration to u limits, or do you want to do that at the end? All right. So if x is 3, then u would be 3 cubed plus 9, which is 36. And if x is 0, u would be 9. So remember, if you have changed these to u limits, you don't have to put x back in ever again. So this would be 6 pi times the integral from u equals 9 to 36 of du over the square root of u. Or remember, that's equal to u to the negative 1/2 du inside that integral. So when we integrate it, we will have 6 pi. The integral of u to the negative 1/2 is u to the positive 1/2 times 2 from 9 to 36. Or we get 12 pi times 36 to the 1/2 minus 9 to the 1/2. Which is what? 6 minus 3 is 3 times 12 is 36 pi cubic units. Sorry, ran out of room down there. Any questions about that? All right. Why don't you guys take about a 5-minute break? We'll pick back up at 1:10. But take about a 5-minute break and then we'll come back and look at some more volumes of revolution. So is anybody still hanging around in here? Y'all's week going okay? Oh, please. Nobody in here should feel that way. And okay, even just the basic integrals, they're just messy. There's a lot of arithmetic and about 473 places to make an arithmetic mistake on these, I know. But it'll get better. You will get better at it, promise. It does help when you do the right problem, though, as I've had apparently a problem with today. Yes. Like, let me see if I can pull this up here right quick. When you go into Gradescope for this assignment, let me show you what the assignment looks like. Well, hang on. My computer is exceptionally slow today. If I can find it. Well, it's thinking, maybe. Okay, so I'm going to try to share this screen right quick. Let me get over there. Okay, do you guys see the, it says at the top, Calculus 2, quiz number 1? Okay, so this is the form that's in Gradescope. So it'll say, problem number 1 is show work from number 1 for your MyMathLab, from your MyMathLab quiz. Show work from number 2, 3, 4, 5, and so on and so forth. Now let's say your submission, when you have done all the work for quiz number 1, you've got a 2-page submission. And it's possible you might have them all on 1 page, which is also fine. You would just identify the same page for every problem. But let's say when you work it out, problems 1 through 3 ended up on page 1, and problems 4 through 6 ended up on page 2. When you upload that submission, it's going to ask you to identify which page each problem is on inside the Gradescope submission. And so that's where you do, it'll just say, which page is this one on? Number 1. Which page is this one on? 1. This one, 2, and so on and so forth. It is in the instructions inside Gradescope when you upload it. And if you want to, I think you maybe, I can try to make it where you could go back in and upload the practice assignment. I think I shut it off yesterday or day before, but I can make it where you can go back in and upload the practice assignment just so you can practice with it if you want. Okay, well, I will double check and I will reopen it. Let me make myself a note. And then that way you can go back in and check and make sure you understand how it's going to work. All right, so let's get back to this. All right, now, I may have lied to y'all. When I hit that, now can you see that it's recording? So in other words, I was wrong. Earlier part of it wasn't recording. So on mine, I thought it said recording, but apparently it did not. But I've got 2 recordings going, so hopefully we'll catch most of everything. And if I missed something, if it was the, homework questions that you wanted, because I don't typically record that on my document camera, but if you missed that, I will send you, I can send you a link to it. No problem. Just let me know. But yeah, Thank you, though, for keeping asking me. Apparently, I should have probably just, I would say just stayed home this morning, but I did stay home. So, yeah, not sure. Okay, going to have to get myself some cheaters, so apparently because I can't see the screen well enough. All right, so let's rotate this region around the x-axis. Okay, does everybody see, because I know that's a little bit small, that's x is equal to 12 times y squared minus y cubed. So that's the graph. We really don't want to solve that for y in terms of x if we can help it. So I would really rather, since this is in terms of y as the independent variable, I want to use horizontal rectangles, right? Because anytime we use horizontal rectangles, we're using an integral with respect to y. All right. If I am going around the x-axis with horizontal rectangles, what method am I using? I am using the cylindrical shell. Yeah. So, with cylindrical shells, when, let's just say this rectangle rotates around that axis, it forms the wall of a cylinder. Okay? To find the volume of that shell or that wall of the cylinder, we need a thickness. We need either a height or length. I think of it as length since it's a horizontal, but it's the height of the cylinder. And we also need a radius. Okay? The length will be this distance right here. The radius will be this distance. Now keep in mind, this little rectangle, it varies as it moves up and down, but for any of those little representative rectangles, they just sit at some y value in the region. And this is y equals 0. So our thickness in this case will be dy. The length will be right graph minus left graph. And that will be 12 times y squared minus y cubed minus 0. And then what will the radius be? Just y. Technically, it's a y minus 0 to keep in it with the idea that we're doing a right minus left or a top minus bottom in this case, but that does just end up being y in this case. So we will have 2 pi times the integral from, the y limits on this region go from y equals 0 at the bottom to y equals 1 at the top. So we'll be integrating from 0 to 1, 2 pi times the radius times the height times the thickness. Now that one, all you have to do to integrate it is multiply it out and integrate term by term. So we would have 24 pi times the integral from 0 to 1 of y times y squared is y cubed minus y times y to the third is y to the fourth. So we would have 24 pi times 1/4 y to the fourth minus 1/5 y to the fifth from 0 to 1. Or that would end up being 24 pi times. When I plug in 1, I get 1/4 minus 1/5. And then when I plug in 0, I get 0 on both pieces. So let's see. 1/4 minus 1/5 is 5/20 minus 4/20 or 1/20. So we end up with 24 pi over 20, or what, 6 pi over 5 cubic units, whatever they may be. It may be inches, miles, feet, whatever. Any questions on that? A lot of times in the homework, they ask you for what the units are. Cubed, squared, whatever. So, you know, when you're doing areas, it's squared, and when you're doing volumes, it's cubed. So sometimes it's very possible that you might have something like that. Yes. Okay, before we do this next problem down here, I want to keep this region for a moment. So let's look, same region. This is 1, this is 0. Let's say I wanted to rotate that around, though I ran out of room up there. Let's call this y equals 2, even though that second unit got really short. What's the only thing about my setup that will change? It would be perfect. The only thing that changes there, I didn't change my region, I didn't change the rectangles that are being rotated. So the thickness is still dy, the length of the rectangles that are being rotated are still 12 times y squared minus y cubed minus 0. But now when this rectangle rotates around this line, it's going to form a cylinder where the radius is going to be this distance. This is some y value. This is y equals 2. So that distance is indeed 2 minus y. The only thing that changed was the radius. So our volume here would be the integral from 0 to 1, because I didn't change the variable that I was integrating with respect to, and I didn't change my region, so the limits aren't going to change. So we'll have 2 pi times the radius times the height or length times the thickness. Excellent job. Go ahead, I'm sorry. Yes, perfect. That was going to be my next question, actually. So if we did have an axis of revolution down here, say at y equals -2, then the radius would be this distance. So the radius would indeed be y minus a -2, or y plus 2. Excellent job. But notice the only thing changing when we change the axis of revolution, unless we reorient our rectangles, if we keep the same direction rectangles, the only thing that changes when you change your axis of revolution is the radius. Good job. All right, so let's look at this one. So this is the graph bounded by the lines y equals 6 minus x, y equals 3, x equals 0. Something's wrong with that. It's 3 minus x, sorry. So this equation is y equals 3 minus x. So this is y equals 6 minus x, and this line is y equals 3 minus x. And they're chopping off the region at 3 and stopping it at 6. So we're really just looking at this little rectangle right here. Now we want to rotate around the x-axis using both the washer method and the cylindrical shell method. Since we just talked about cylindrical shells, let's do that method first. So if we want to go around the x-axis here, using cylindrical shells, we will have to talk about horizontal rectangles. Okay? Now, If we're using horizontal rectangles, the thickness will be dy every single time. And then we need a length or height of the cylinder and a radius. It would be. That is no, but I want you to be aware of what it is because I'm going to add something to it here in just a minute. So for this particular part, we've got a boundary here of 3 minus x, a boundary of y minus 3. So you're right about that part. This region just stops at y equals 3. Absolutely. But I want you to keep in mind that this is the line y equals 3 minus x. If we need it for something, which we will in just a moment. Okay, but not for this part. I got ahead of myself again, didn't I? Okay, so what's the length? Well, it's got to be in terms of y's, first of all. So this is y equals 6 minus x, so that's x equals 6 minus y. Right minus left would be 6 minus y minus 0. And what about the radius? What's that distance right there? Almost. It would be y minus, but it goes all the way down to the axis of revolution. So it would be y minus 0, or just y. We're going to take into consideration that 3 when we set up our limits of integration for this region. The region only rotates from the region extends, I should say, from y equals 3 to y equals 6. Because, as you said, that is y equals 3, and then the other line's 3 minus x. So we would have the integral from, for this particular shaded region, it goes from y equals 3 to y equals 6, 2 pi times the radius times the height / length times the thickness. Now, that would be a pretty straightforward integral to do, right? We just multiply it out and integrate it term by term. So it's not difficult to integrate that one in terms of y. Now, the other option they asked us to consider was to do the same problem using washers or discs. So, go ahead. Now, this line right here is the line y equals 3. We're rotating around the x-axis. Y minus 3, what I said earlier. Correct. If we were going around this line, then that distance would be y minus 3. Let me erase this part for just a second. I think I may be confusing you with all my little markings there. Okay, if you rotate this rectangle around this axis, it's going to come down here, and we're going to form a cylinder. Okay, yeah, I think it helps when you actually, even though that's a terrible cylinder, I should have drawn one in. But the radius is the distance from the center of that cylinder, which is always the axis of revolution, to one of your little rectangles. So that's why it's a y minus 0 instead of a y minus 3. Exactly. Yes, we don't have to take into consideration an outer or inner radius here. That part, as you said, is completely dealt with by the limits on our integral. because the region rotating only starts at y equals 3 and goes to y equals 6. Excellent. So that I don't muddle that picture up anymore, let me draw it again down here. So this is y equals 3 minus x. This is y equals 6 minus x. This is the region under consideration. So this would be 6, this would be 3, and we're rotating around the x-axis. Okay, the other question was, what if we wanted to use discs or washers? Around the x-axis here, if we wanted to use discs or washers, we would have to use vertical rectangles, because remember, they have to be perpendicular to the axis of revolution. So would we be using discs or would we be using washers? It would be washers because the axis of revolution is not a boundary line of that graph. Now, if we wanted to use washers, we need a thickness, an outer radius, and an inner radius. Anytime the rectangles under consideration are vertical, your thickness is dx. The outer radius will be the distance from the axis of revolution to the furthest of your two graphs, and the inner radius will be the distance from the axis of revolution to the closer of your two graphs. Remember, the inner radius is basically just the radius of the hole. So we would have this distance, top minus bottom, would be 6 minus x minus 0. And inner radius, in this case, all of those bottom graphs hit at 3 down to 0, so that would be 3 minus 0. Because all of these rectangles sit on the line y equals 3 for this particular shaded region. So we would have pi times the integral from what to what? Well, the x limits on this region go from here to here, so that's going to be x equals 0 to x equals what? Well, if this is y equals 3, we would have 3 is equal to 6 minus x, so x is also equal to 3. So we're going to be integrating from 0 to 3. Pi times the outer radius squared minus the inner radius squared times the thickness. Now, what should be the relationship between that answer and that answer? They better be equal. And if you get something different for one of them, then you know you did something wrong. And both of, oh, go ahead, I'm sorry. Where are you looking? Oh, no, not in this case. This line is 3 minus x, but we took into consideration the fact that it stopped here by using our inner radius was 3. Okay? I shouldn't have muddled it by putting y equals 3 minus x here yet, because we're about to use it, but we didn't have to use it in this particular part. Because that graph, they could have just not even drawn a picture of any bit of this part. Sorry, I know that's shaking the camera and giving you a headache. I apologize. But they could have just said y equals 6 minus x is here, and this is y equals 3. So it's this region that we're rotating on this particular problem. So since that region doesn't reach down there to the y equals 3 minus x, you don't have to consider it. Does that make sense? Or am I missing your question? Okay. Okay, I'm going to give y'all a couple minutes to make sure you've got that written down, or at least a couple seconds, and then we're going to look at the other part that I wanted to do on this particular region. All right, so this time we have the same graphs that we started with. This is y equals 6x, this is y equals 3x, this is y equals 3. But I just have a parallelogram here that I'm rotating. Let's rotate it around the x-axis one more time, and then we'll start shifting our axis of revolution. If I just asked you, which method do you think would be easier for this problem? Vertical rectangles or horizontal rectangles? Why? I agree with you 100%. Perfect. If we were going to do vertical rectangles, notice that over here the top graph is 3 and the bottom graph is 3 minus x. But over here the top graph is 6 minus x and the bottom graph is 0. And it's even conceivable, depending on the graph, that you might have had some where you had the top graph be 6 minus x and the bottom graph be 3 minus x. This one didn't have that because of the symmetry of the graphs. But anyway, it would be much easier to use horizontal rectangles because we'd only have to set up one integral. The difference is we are going to have to switch these so that x is the dependent variable and y is the independent variable. So we want to think about this as x equals 6 minus y, and this one would be x equals 3 minus y. Okay. Since those rectangles are parallel to the axis of revolution, we are by force using cylindrical shells. So we would have to find a thickness, a length of the rectangles, and a radius. The thickness in this case is dy. The length is right minus left would be 6 minus y minus the quantity 3 minus y, which is what? 3? Now why is that? Why do I have a constant length for all of those rectangles? It's because the lines are what to each other? They're parallel. They have the same slope. So they just, all of the rectangles from one to the other will have the same width because they're the same distance apart all the way up. But okay, as I throw my pen across the room accidentally. Okay, so what about the radius? When this rectangle rotates around this line, it's going to come down here and it's going to form a cylinder. Okay, the radius of that cylinder, I went just a little bit farther, is the distance from that wall to the axis of revolution. So it's going to be some y value minus 0, or we would just have y minus 0. And in this case, our volume would be 2 pi times the radius times the height slash length times the thickness integrated from this region goes from y equals 0 on the bottom to y equals 3 on the top. I cannot overemphasize how important it is to have a graph of the region. And guys, don't be lazy as far as drawing stuff in. Draw yourself in a rectangle and identify what's the length, what's the radius, stuff like that. It really can help you a lot. Okay, so what about this? So I have one region and we're going to rotate it about a lot of stuff. The region is bounded by y equals x squared, y equals 0, which is the x-axis, and x equals 1. So first things first, let's draw our region. Doesn't have to be a perfect graph, just has to be a pretty good representation. So there's the y equals x squared. Y equals 0 is here. X equals 1 is over here. So the region enclosed is this little guy right there. Okay, so it only goes over to the right. Now you don't have to erase that if you don't want to, but okay. All right. We want to rotate this around the x-axis. If I didn't specify, and I am prone to not specifying, I usually let you pick your favorite most of the time. What method would you prefer to use if we were rotating this around the x-axis, do you think? Let me add, oh, go ahead. Absolutely. This one, it's kind of 6 1/2 dozen of the other in a lot of ways, but since the function is already written as a function of x, I would probably rather use vertical rectangles. And this graph is vertically simple. In other words, we have a consistent top graph and a consistent bottom graph. Y equals x squared is always on top, and y equals 0 is always on bottom. Okay, if I use vertical rectangles around the x-axis, what method am I using? Disk method. Excellent. So I need a thickness and a radius. The thickness, anytime you're rotating vertical rectangles, is dx, and the radius is just the height of those rectangles. So that would be x squared minus 0, or just x squared. So we would have pi times the integral from 0 to 1. I didn't write it down, but that was specified as x equals 1 in the statement of the problem. So we have pi times the radius squared times the thickness. Now, if I switched that and asked you to go around the y-axis, do you want to change your rectangles? Probably not. Once you have a good rectangle that's going to work as far as it's giving me only one integral to set up, unless you get it set up and you go, well, I just don't know how to integrate this, I would keep it with the same variable. So what if you want to go around the y-axis? If I'm keeping these same rectangles, I am now using cylindrical shells. So the thickness is still dx. It always will be if you're using vertical rectangles. The height is the height of the rectangles being rotated, which is still just x squared minus 0. And the radius, if that little rectangle rotated over here and formed a cylinder, the radius would be this distance right here, which is this little x value minus this little x value, which is x minus 0. So we would have the integral from, still from 0 to 1, because I didn't change the region or the variable that I'm integrating, so I don't change the limits, but we would have 2 pi times the radius times the height times the thickness. Now once again, guys, it doesn't matter if you put that 2 pi or the pi in front of the integral or inside the integral. Sometimes I do one way, sometimes I do the other. You're going to factor it out eventually anyway. All right, I want you guys to take just a minute. Well, actually take about 5. And for that same region, I want you to set up rotating around the line x equals 3. So we've still got this region. This is the point 1, 1. But here we're going to go around x equals 3. and then also around the line y equals -2. Okay, so see about setting those two up, and then we will compare. Did I tell y'all about making sure that you're in Zoom with your first and last name? I think I did, didn't I, last time? Oh, everybody is. We're all good. I just need it that way so I can do roll. But okay. When you get an answer, and these are just setups on this one, feel free to type in the chat that you're done, and I'll know, kind of when we can start talking about it. All right. I know you're still working on it, and that's perfectly fine. But I want to make sure we get the answers up here before time is up. So if I stay with my vertical rectangles around the line x equals 3, what method am I using? Shell method. Excellent. Okay. Now, the thickness, still dx. The height of the rectangles that I am rotating is still top minus bottom, or x squared minus 0. But now the radius would be this distance right here. Because the axis of revolution is always the center of the solid, and so the distance for the radius is always going to be measured from the axis of revolution to something else. So in this case, that would be a 3 minus some little representative x value. And we would have the integral from x equals 0 to 1 of 2 pi times the radius times the height times the thickness. Is everybody okay with that? Okay. What about y equals -2? Once again, I've got my vertical rectangles. I don't really want to change them. So in this case, my rectangles are perpendicular to the axis of revolution, but the axis is not a boundary of the region, so I will be using washers. So I need a thickness, which is still dx, an outer radius, and an inner radius. The outer radius will be the distance from the axis of revolution to the furthest of your two graphs that comprise the top and bottom of your rectangle. And the inner radius will be the shorter of the two distances. So the outer radius would be top minus bottom, which in this case would be x squared minus a -2, or x squared plus 2. And the inner radius would be 0 minus a -2, or 2. So our washer method would give us a volume of the integral from 0 to 1 of pi times the outer radius squared minus the inner radius squared times the thickness. Now be very careful when you are doing washer methods that you square each radius separately. It's never going to be outer radius minus inner radius and then squared. It's always going to be outer radius squared minus inner radius squared. Okay, questions? No, these guys, these were going around different axes, so these volumes would not typically be the same. The only time we had the same one is we did a problem, which I have put somewhere else, where we were doing the two different methods for the same region. Here, we were rotating the same region about the same axis, but we were using shells on one and washers on the other one. Those two should be equal, because that's the same problem, just using a different approach. These guys that we just did, we actually have the same region, but it's rotating about different axes, and so the volume generated would most probably be different in all four of those cases.